the last talk of the workshop, we have Philipp Hauke, who will be talking about applications of tensor networks for stimulating strongly correlated quantum systems.
Yeah, thanks a lot for the kind introduction, and thanks a lot to the organizers for inviting me here. Yeah, to present some of the things that we are doing. Yeah, so it's really a pleasure. It's also the last talk, so it's an honor to do that. Yeah, so this talk is going to be more, let's say, of a bit of an overview talk. Also, it's a bit of an heads up. We are not a group who's developing heavy numerics tensor network schemes, but rather we are using them as applications. Okay, so and I want to show you some interesting application areas where we're using them. But before that, because I'm also the director of the Quantum Center QATN here at Trento, I feel I have to do a little bit of publicity for that. So here, this is the beautiful view of Trento, and over there, up here, we have Povo. Don't have a pointer, right? Okay. And here, there's of course the University of Trento with the Department of Mathematics, Physics, Computer Science, and so on. But we also have the INFN, CNR, Bruno Kessler Foundation. Over in Vilazzano, very close by, we have the ECT STAR. And so this means there's actually a huge density of different institutes and departments working on aspects of quantum science and technologies. So in 2018, we decided that would it not be a good idea to join efforts, to join human resources and infrastructures to build something bigger. And this is when we founded QATN, Quantum Science and Technology at Trento. And we are active on all aspects of research in quantum science and technology, from very, very fundamental to very applied experiments, etc. We're also active in technology transfer, scouting of new technologies, patenting, etc. And also in education. So we have, for example, a transdisciplinary PhD program in quantum science and technology, where some people here, like Otto, are members. So I think Trento is a perfect place also to do a workshop like this. It's a very, very stimulating environment in general. Okay, enough about that. But so now, okay, let's talk about applications of tensor networks. Just to set the stage a little bit, what we're after, we want to understand quantum many-body problems. And this is actually something that pervades all of the physical sciences. So from elementary particle physics, how do elementary particles like quarks and gluons interact? How do black holes emit radiation? That is a question for cosmology. What types of materials can we have? How do we need to cook up the different chemical elements to get a certain transport properties and so on? Which chemical reactions can occur and so on. So it's something, and all of these are described by quantum many-body systems that we would like to understand and solve. Now, solving them, what does it mean? Well, we write down the microscopic model that we think describes these systems. And sometimes they can look deceivingly simple. For example, for elementary particles, we want to write down the Lagrangian of quantum chromodynamics of QCD. And you see it's a very compact formula. There's some size describing the fermions, and then there's some gluon field. Similarly, if we want to talk about materials, the workhorse is the Fermi-Hubbard model. We've seen also yesterday discussions about the Hubbard model, right? So we have just electrons moving on a crystal lattice and they can interact. So this looks all very, very simple microscopically, what happens locally. So these guys, they move and then they interact. This we can write down very, very easily. So it looks deceivingly simple, but of course we know that if we want to actually solve these equations, the curse of dimensionality kicks in and the Hilbert space grows exponentially with the number of particles, right? Now, one can wonder, but still, why don't we just solve a building block and then we are happy and understand what's going on? Well, the problem is that this is not how complex systems work. So if you look at the textbook definition of a complex system, by various properties, I just want to highlight two. Well, typically they show some type of nonlinear or chaotic behavior they will do. And this then in turn leads to something we call emergent behavior. So the whole is much more than the sum of its parts. And this has been discussed, for example, in this very nice article by Philip Anderson. So if you don't know it, I invite you to read it. More is different. That's a very also interesting and stimulating read. Okay, but so now we can wonder, okay, so now we have complex systems. Does this mean that, so we cannot just look at building blocks, but does it mean now we need to solve the entire thing? So if we want to look at the material, we need to solve now something that has Avogadro number of particles, 10 to the 23, to understand what the material does. Luckily, this is also not what we have to do, because there are very powerful theories like the universality, critical scaling, and this allows us usually to do from relatively small systems finite size extrapolations. And so we can understand what happens for very large systems. Okay, it's not enough to look at the single building blocks, but if you get the systems a little bit large enough, we can extrapolate, and then we know what happens if you have essentially infinitely large systems. Okay, and that's something that is not automatic, I would say. So there's some undecidability proves that in general you can cook up systems where this extrapolation does not work. There's no way that you can do an extrapolation, but the physical systems that we find in nature, they behave very nicely, and you can do this extrapolation. Okay, so now then, what can we do about this? How can we solve these systems? I want to talk, of course, about tensor networks, but just to put it a little bit into context, I want also to discuss very briefly other methods. So one thing that we also in my group we use very heavily is exact diagonalization. So you just take this big Hamiltonian there, this huge matrix that lives in the Hilbert space, and then you just diagonalize it, find the eigenvectors, eigenvalues, and then you're done. So this works in principle always, but only for very small systems. So just to give an idea now, so if you have spins 1/2, we can do like 30 up to 40 spins, depending of the symmetries that we can use. But if you want to solve QCD, then we need quarks, we need gluons, we need different flavors and all these things together. So we cannot essentially not even solve a single cube of QCD with exact diagonalization. Okay, so it's very powerful for the small systems that we can handle, but it's very limited. Sometimes, of course, we have analytical methods. So we have free fermions, free bosons, or if we can do perturbation theory, then we can go to large system sizes. And a very big workhorse is, of course, quantum Monte Carlo. So when we can use this, we can treat very, very large systems. But it has it solves quantum mechanical problems by sampling methods. But then, since we have complex amplitudes, we can get the sign problem, which happens for fermionic systems, or if we have frustrated magnetic systems, and then we cannot use quantum Monte Carlo. So I would say essentially, where we can use it, it is the method of choice, because we can go to very large systems, but then there are systems where we just cannot use it, like the Fermi-Hubbard model that we saw before, also for time evolution. Okay, so these methods, so when they work, they're essentially exact, but there's also some expansion methods, like semi-classical methods, which expands in 1 over h bar, and mean field methods. So so mean field just truncates any correlations, any quantum correlations. Semi-classical methods truncate quantum fluctuations. Okay. So also then they can treat very large systems, but they limit quantum effects. And so maybe I would say that tensor networks are somewhere in between, because they also limit quantum effects in some way, but in a very, very controlled way, of course, much beyond the mean field. And then when they work, they are also essentially exact. No? So as we have seen, tensor networks, they have difficulties in higher dimensions and in highly entangled regimes, but they're of course very versatile. And I just want to point out, I mean, you know this, but I want to stress this thing that we have a very clear control parameter given by the bond dimension. So we can know when you can fully trust the method. And this is different from other expansion methods where sometimes you can have, for example, in a perturbative expansion, it looks like the perturbative expansion is converging, but then higher order contributions can actually blow up. Yeah? So it's very hard to rigorously say when is an perturbative expansion actually convergent. And here we know we have the bond dimension, so if it's not saturated, we know that the method works. Yeah? And I also want to point out that on the other hand, if we know that it breaks down because we saturate the one dimension, we also still learn something, because then we know maybe it cannot describe the state anymore, but we know that we can that is a highly entangled state. So we also learn something about the physics of this of the state that of interest. Okay, so now where do we use this? So I mentioned already different types of many-body systems, but another application area that I also want to discuss a bit is actually to benchmark quantum computers and quantum simulators. Yeah, so we can use them to describe some circuit implemented in a superconducting qubit device, for example. And it's actually useful for various points of view. So we can certify that the quantum hardware works as it is expected, to just cross benchmark, okay? But we can also use this to identify which type of quantum effects do we expect in the quantum computer. Where does the quantum computer actually build up entanglement? What quantum effects do we need able to produce? And one thing that I think is also very important, that having on the one side the tensor network, on the other side the quantum computer, this is a very strong cross stimulation between the two. Yeah, so it's both. So I've seen this many times, that quantum computers, of course, they want to proceed into a regime that is beyond capacities of classical computers, and then someone comes up with a better tensor network code, and then still can reproduce what the quantum computer does. So they are really stimulating each other and pushing each other forward, which I think is a very good thing. Yeah. So now, what I want to do is, for the rest of the talk, I want to give you two examples where we apply these things. Yeah? So the first example is in this area of benchmarking quantum computers, in particular, understanding the role of quantum effects in quantum computations. And then I'm going to give an example from many-body systems. Okay, so this work is done mainly by Chiara, Gopal, and Alberto. And so let's see what it's about. So, okay, so what are we here after? One use case of quantum computers is to solve hard classical optimization problems. So, and hopefully, of course, faster than a classical computer could do this. Now, one way to do that is, so in the quantum computer, we have qubits available. So one way to solve classical problems is to write them as an Ising model. Okay, so we have some qubits, which are now just sigma z interactions, and we want to find the ground state of this model. Now, why is this interesting? Well, because one can show that all decision problems that are in the computational complexity class NP, okay, so non-deterministic and polynomial time on a Turing machine, which means these are essentially all problems that we usually treat that are hard, like a traveling salesperson problem, things like this. Yeah? And all of these problems can be reduced to deciding whether the ground state energy E0 of an Ising model is beyond a certain value or above a certain value. And the B minus A, they are separated by what one calls the promise gap. Okay, so we need to be a little bit of space, because otherwise I need to be able to say something that is infinitely fine, which is beyond, so which makes things blow up too much. Okay, but essentially, if I have any optimization problem, I can write it as an Ising problem and then say, is the ground state energy beyond a certain value? I just want to give you two examples. So for example, one can do this for things like, okay, you want to optimize what is the charging schedule of a fleet of electro vehicles. And then I don't want to go into the details because it's a bit tedious, but essentially we can write down Ising degrees of freedom. So for the different electro vehicles, what is the charging level? And then we have different charging stations, and we can say 0, 1 is the station occupied or empty. And then we can write down a cost Hamiltonian for this, where we have some, the local fields are essentially, if you're charging, how much does it cost? And then one can have easing interactions, so not two vehicles can be at the same charging station, so they have a repulsion, so to say. Yeah? And then you can write down an easing model for this. Or another example is the question, how precisely does an unfolded protein acquire its folded structure? What you've shown in this paper here is that we can write down this thing as a graph problem. Okay, so this is the protein that we want to know how does it go from the unfolded structure to the folded one, and we want to know which structures does it visit in this dynamics. Okay? So it's a little bit, one has to cook this thing a little bit. We don't need to actually compute the dynamics, but we solve a graph problem, and then we can write down this as an easing problem by introducing binary variables. So on each link, we put a variable 0, 1 if the protein goes through this configuration here or this configuration, okay? And so then these links here are in the state 1 and the other links are in the state 0. Then this means we take this path here. And then one can write down an action principle for this, where we minimize the action of this this dynamics, which boils down to find the shortest path across this network. And this is then a minimization problem on easing variables. So we can write down this thing as an easing problem and find the ground state, which gives us the shortest path. And then one can look at things like this. So this is the unfolded initial structure. And then we see how it goes from one vertex to another one, and each vertex is a new configuration. And we can see the dynamics that this protein takes, and then it reaches the final folded structure. Okay. But now, how do we find, so we want to do this actually on a quantum computer. So how do we find the minimum of this cost function? And so one way is to use what one calls the quantum approximate optimization algorithm. And so the main idea is that we get a trial wave function, which is parameterized by some angles, gamma 1, beta 1 to gamma p, beta p. And then we optimize these angles in such a way, so the variationally, such that we get the state should get close to the ground state of this cost Hamiltonian, which would be the ground state of this easing model that encodes the problem. And well, if we are close enough, then we have found the solution. And so one very typical procedure that one does is one starts in a tensor product state of everyone polarized just in the x direction, and then one applies the cost Hamiltonian, then something that does not commute with the cost Hamiltonian, the so-called mixer, and so on, and then alternatingly, and with different strengths, gamma 1, beta 1, and so on. So and then so we explore different states. So essentially, this is the circuit according to this. Okay, so we initialize all first in zeros, then apply the Hadamard gate, so we get a tensor product of all in the plus state, and then we apply cost Hamiltonian, mixer, and so on. And in the end, we measure. And the nice thing is, so the cost function is just a classical easing model, so we can measure in the diagonal basis. So we just get the configuration, which is up, which is down, or which is 0, which is 1, and then we feed this into a classical computer, and one can run some classical optimizer that gives us back the updated variational parameters, and one runs the cycle a bunch of times until we get closer and closer to the ground state. Okay? Again, so the nice thing is, let's say the idea is that by using a quantum computer here, I can explore highly entangled states that I would have difficulties to put into a classical computer and do a similar variational ansatz on a classical computer. Okay? Okay, but now one question that one can ask is, okay, we start actually in a non-entangled state, no? This is just all plus. And we want to go to the ground state of a classic leasing model, which is again completely non-entangled, classical. So that one can wonder, to do this, to reach good solutions, do we actually need much of entanglement or other quantum effects? What role do the quantum effects actually play in this algorithm? And so to test this question, what to do is we simulate this algorithm using MPS. So we put in now, one can also take a specific optimization problem. Here we just take, so in principle, we would like to just take a random Ising model, a Sherrington-Kirkpatrick spin glass, and we capture all types of Ising models that you can think about. But because this is hard in tensor networks, we restrict ourselves to third neighbor interactions. Okay, but still we take, so we have an Ising model with random interactions up to third neighbors. And we just, so how does one, can one treat this? Is actually quite easy. So we do just, because they're long arranged, we want something that is short range, but it's actually quite easy to treat this. So we just, so if you want an interaction between, Ising interaction between 0 and 3, we just apply a swap gate, swap until we get the 2 qubits to nearest neighbors, then apply a nearest neighbor interaction, then we swap it back. And so this increases a little bit the circuit, but we can treat longer range interactions also very efficiently in this way. And okay, so now we want to use this to characterize the quantum features, quantumness in these models, okay, during this circuit. No? So during how much, if you do this to get a good solution in the end, how much quantumness to build up, or could you also do the same on a classical computer? It's essentially the question. So the first thing that I of course look at is the entanglement entropy, which tells us, of course, how difficult it is for tensor networks. But also for quantum computers, it's important because it tells us how many CNOT gates do we essentially need in this circuit. What is nice, if we simulate this thing with tensor networks, we get this number essentially for free. But another marker that we have been looking at is actually comes from the geometric measure of entanglement, and we've seen this already yesterday in the talk by Harm Derksen. So I just want to briefly remind ourselves, what is this actually? So what we look at here, so instead of the entanglement entropy, we look at the distance-based measure. So if we have the set of separable states and want to know how much entangled is the state of interest, and someone can look at the distance to the set of separable states, which is then the geometric measure of entanglement, and in formulas, it looks like this. So the set of separable states is are the states of tensor rank 1, so the Segre variety. It's not a language that we usually use, but yeah, but I think it's good to do these connections. Okay, and then one can, the geometric entanglement can be defined like this. We maximize over the overlap of the state of interest to all separable states. And then now this looks at first like a very difficult optimization problem. Now we have the entire set of states we need to optimize over. But in reality, for pure states, it becomes very simple. Because so if we write down the state psi in the Schmidt decomposed form, we take the overlap here, then it's just the maximal Schmidt coefficient squared, which is essentially the spectral norm. And okay, so that's very nice, and it becomes actually quite treatable. Now, I want to go a little bit beyond this, because if we look at multipartite systems, so I don't only want to distinguish some space A from another subspace B, but I want to treat all of these, let's say, qubits or whatever on the same footing. So I need to really look at a multipartite system. So we need to go beyond the geometric measure. And there's the so-called generalized geometric measure that we're going to see in a second. But just to give an idea, why is this not the full story? Of course, if we write down, let's say we have 5 qubits, okay, C2 to the 5. If you write down a single Bell state across the cut of interest, now we can calculate what is the geometric measure of entanglement. Okay, we have here, we get out, if we plug in the numbers, 1/2. Okay, so this is the maximum that you can actually have. But if you look, for example, at the GHZ state, which is all are in 0 or all are in 1, they have the same tensor rank, these two states. So if we write this out, we get also 1/2. Yeah? And so this means, okay, somehow, but now I would say, okay, if I look at these things that dangle here around, I would say this is somehow more entangled, or it's more multipartite entangled than this state here. Okay, so one can actually use this intuition to generalize to the generalized geometric measure of entanglement, GGM. And so the idea is the following. So instead of looking at only separable states, one actually starts with the n separable state. So this is a pure product state of all parties. Yeah? And then we have different types of entangled states around. And for example, this state here would be 3 separable because I can separate the system into 3 parts, 1, 2, 3, right? And this state here would be 2 separable. If these 3 are entangled, these 2 are entangled, but I can cut here. And then this state, the GHZ state, for example, would be n particle entangled because I cannot cut out any one. And so one can really make different sets, and then from this look at the distance to these sets. And the GGM, actually there's a hierarchy that we can define the distance to any of these sets. And so they call the GK. So Gn would be the distance to the n separable states. The one that we look at is G2, which is the distance to the 2 separable states. And this means that I look at now not only the cut here, but I look at any cut. And then I say, okay, what is the maximum, what is the distance to any state that I can cut somewhere? Okay, so this is separable across any bipartition. And so this would be, okay, this definition here. No? Okay, so I take the overlap of the state to any state that is separable across any cut AB. Again, this looks like a very difficult optimization problem, but it's actually not so hard because, again, we can use that this is the maximal Schmidt coefficient, but now I have to also maximize over all possible cuts. And if the system becomes very large, so this means I have to simply find the maximal Schmidt coefficients across all bipartitions. But of course, if it becomes very large, the system, then there are many, many bipartitions that in principle one would need to check. So, by the way, so I'm, I don't know if one can also this GGM, probably one can use the same techniques that you've seen yesterday to also generalize some things, say general things about the GGM, which could be also interesting from a mathematical point of view. Okay, and so this measure, this now measures what we call genuine multipartite entanglement, because now if this is non-zero, then all particles are entangled. I cannot take out any one. Okay. There's another measure that we are looking at, because so entanglement is very, very nice. So I like it a lot. I've worked a lot on it, but actually entanglement alone is also not enough. So yes. Uh-huh. No, I'm looking at what is the so I look at the distance to all separable states that could be cut anywhere. Okay, so instead of fixing, yeah, exactly. Yeah, exactly. No, but this is just so now what I'm just looking at is this is an example of a 2 separable state because I can cut it here. But then so I test how much am I distant to these type of states, and then I have to test also what happens if I cut here. So A is only 1, and then the other 4 if I cut here, and so I have to take all combinations that give me A and B. Yeah, no, thanks. Yeah. Yeah. Yeah, so this is again very nice, but it's not enough. There's actually massively entangled states that are still easy for classical computers. And so if you think about now in this context of quantum computation, it becomes important because we want to know, can the quantum computer outperform a classical computer? And, so we need lots of entanglement because otherwise I can easily describe it on a classical computer, but I need also more. For example, give an example, there's the ground state of the toric code, which is given by all, so you start with all zeros essentially, and then you apply loop operators and make a massive superposition where you've applied all loop operators to flip things across different loops. And this is a massively entangled state, but actually it turns out that this state can be easily described simply. And so in general, these types of states, actually this is called Gottesman-Nil theorem, which tells us the following, that if we have a quantum circuit of this type, so I start all in 0, and then I apply operations from the Clifford group, so Hadamard's, C-naughts, and S-gates, so these are pi half rotations, and I get the final state out. This state, there are lots of C-naughts in here. This can be a highly entangled state. Yeah? But it's easy to describe this state classically. And one reason is that the number of states that I can visit in this way, they're exponentially many, but there's only a discrete countable number of states. So for example, for a single qubit, if you can, with H and S gates, you can visit all the cardinal points of the Bloch sphere. But you cannot go arbitrarily to arbitrary points on the Bloch sphere. And you can generalize this to larger and larger systems. So there are many, many states that you can visit, but they are countable and a discrete number. And then one can use this fact, and one can write down so-called stabilizer tableaus to actually to keep track of the state that one is in, and then one can compute it easily. These types of circuits, they are very interesting, but they are not universal for quantum computing, which we can, well, maybe understand, or at least it's good that it's the fact, because if these are easy for classical computers and they would be universal for a quantum computer, then we would have shown that a quantum computer cannot do anything more than a classical one, right? So they're not universal. And what is also an interesting point, maybe to point out, is that this type of Clifford circuits, if I apply them to a Pauli operator, so I have a string Paulis, okay, so a rank 1 tensor, and I apply the Cliffords, what I get out is again a string of Paulis. So the Cliffords, they cannot increase the tensor rank of the Pauli operators, which maybe shows us that they're somehow easy. And okay, so now what do we need? Well, what is missing are actually the T gates. So if I need to put in some more non-trivial phases, if I have these rotations here, then suddenly I can build combinations of H and T gates such that I can visit any point on the Bloch sphere arbitrarily closely. And then I have a continuous set, and things become very difficult for a classical computer. And in fact, the Gottesman-Nil theorem tells us that if I sprinkle in a bunch of T gates in the circuit somewhere, okay, then the state that comes out becomes exponentially difficult to treat on a classical computer in the number of T gates. So I can still use this sort of stabilizer tableau calculation, but if there's no T gates, it's polynomial in complexity. If there are T gates, it becomes exponential. And what is also interesting, actually, so for, let's say, for C-naught gates, we see that they are, well, C-naughts are difficult for quantum computers in the current era, but also difficult for tensor networks. Something similar happens here. These T gates, they are difficult for classical computers in this stabilizer tableau calculation, but they are also difficult for early fault-tolerant machines, because in a surface code, I cannot do the T gates in a transversal manner. So they actually, the C-naughts in the surface code, the C-naughts become easy, Hadamard's are easy, but the T gates are suddenly very hard. So it's an interesting fun fact. Okay. Yeah, these type of states that are generated in this way are so-called non-stabilizer states, whereas states that are generated by the Cliffords are called stabilizer states. And so one can compute this non-stabilizerness, so how many T-gates are in there, which also some people call magic, because you have, so entanglement, you need to make a quantum computer work and so on, but there's some magical ingredient still missing to make it fully universal and maybe outperform classical computers, and this is this non-stabilizerness. So people like to call this thing also magic. Okay, and so this, in some sense, this becomes a resource for quantum computing. One can actually write down a quantum resource theory, such as the resource theory for entanglement in the same way. Okay, how can one quantify this? We can build also something called that is called this stabilizer Renyi entropy, which looks in the following way. So this Renyi entropy of the state psi looks at the overlap of with the Pauli strings of the state, and then there's a normalization factor, and we take the lab 2 to the q. And so if the state is a stabilizer state, we can use this fact for a second. We can use this fact here. If the state is a stabilizer state, I know that it's generated by Cliffords acting on the zeros, and Cliffords acting on the Pauli strings give another Pauli string. So I pull out the C's here, and then I get P prime. So it's just the same as having the expectation value of a Pauli string in 0. So I can use this, and this holds for any stabilizer state. So I can use this to show that there are exactly 2 to the n Pauli strings that give me an expectation value of 1, or a -1 actually should be there. So if I have only 1s and sigma z's, then I get a 1 expectation value. If I have somewhere an x or a y, then I get a 0. And then, okay, I'm rotating this into different other Pauli strings for different stabilizer states. Okay, but so there are exactly 2 to the n that are non-zero. This is the minimal number. I plug this in, and then one sees that in this, what comes out is is 1 here in the sum. The log takes it to 0. So this number for stabilizer states is 0, and for other states it becomes non-zero. Yeah? And so this is actually really a measure in the sense of resource theory for this non-stabilizerness, and it is really related to the number of T-gates that one needs to generate the state, as Lee and Yu have shown. Okay, there's one interesting feature to point out. So if you want to compute this thing, because in principle, how many Pauli strings are there? P in the sum, well, there are 4 to the n. So I can choose between x, y, z, and identity everywhere. Okay, all identities I don't need to evaluate, but the rest I need to evaluate all of them. So this becomes prohibitively expensive very, very soon. But actually what one can show is that one can efficiently sample the different Pauli strings on the polynomial number and still get a very, very good estimator for this number m. Which has been shown in this paper in the group of Marcello Del Monte and co-workers. Okay, so this means on principle, it's a very, very costly thing to evaluate, but in practice, we can actually do this also for relatively large systems. So that's nice. Okay, so now we come back. So now we want to evaluate these things in this variational circuit here, which gives us the ground state of some easing problem that we want to solve. And this tells us how does the protein fold, or how should we most cost efficiently charge our electro vehicles or something like this. Okay, so now we compute this using tensor networks. And so we can look at both entanglement and non-stabilizerness. So first, there's actually from one paper where we computed entanglement. What we see, so here is, so this is actually I think this plot is for the von Neumann entropy. We have also the GGM, but it looks similarly actually. Okay, so what we do here is we look at, this is the progress during the circuit. and we have different numbers of layers. So we have do this actually here with exact diagonalization. So we have a very, very large numbers of layers, like 5,000 even. Okay, and so here's this, so the initial state, and then we go through the circuit, and then the end we measure, okay, the progress. And yeah, sure. Yes.
For the qubits, I guess log 2 is like essentially what.
Uh-huh.
Because the target state you're looking for is the product state basically, so it has zero entanglement. Also,
yeah,
complicated states, but they don't.
Yeah. Yeah. Actually, so let's think for a second. So the so this thing here, yeah, even the smallest one is relatively deep, no? So you have 100 layers there. So yeah.
You need them, like,
Yeah.
but they don't, like, from the
Yeah.
point of view.
No, this, yeah, I guess it shows us that this thing here we could also somehow solve on a classical computer, I would guess, because there's, yeah. But this is, so it's also, so I don't know if the number is too, if it tells us too much, because it's also, this is a very small system, no? So we have just, so actually what one should look at here is how does the entanglement scale? You know? And so in other problems, we have seen that so that in the interesting regimes where we expect a quantum speed up, that entanglement actually scales with system size. So then, which means that at some point it becomes prohibitively large. Yeah. So maybe this is okay. To make this point, one should probably look really at the scaling behavior. Yes, exactly. So this is actually this is an interesting observation, that actually this maximum is also not so much what tells us about the success probability. No? So the mostly what happens is that so by the way, so this actually okay, I glossed a bit over. This is more like a so we start from an annealing schedule and then optimize a little bit. So it's a little bit a different setting. It's not exactly the Quaoa setting that I've showed before. The other plot is going to be, but actually, so essentially what happens is that so there is a maximum that we need to reach, but actually also in different studies we only see that this maximum that you arrive is not very much correlated to the success probability in the end. So it seems that generically, whatever you do, you build up lots of entanglement. Well, we have lots of entangling gates somehow in there. What is, I don't know, okay. What is correlated to the success probability, the darker curves, which have reached the ground state much better, is they get rid of the entanglement. So they all take the same initial growth, but then they manage to get rid of this again. And this is somehow where the where the circuit needs to work. Huh? Exactly. But so generically, if you go too fast through a quantum annealing or do the too few layers in a Quaoa, you don't get rid of the entanglement in the end. So you have a superposition of many states, which means you have also higher states in there, and you don't find very well the ground state. And so it's actually a little bit. This is something where we. So we started these studies in 2015 actually, and in the first we struggled a bit because we were hoping to see that if we build up more entanglement, more quantum features, somehow we get better solutions. But the absolute maximum is not what really counts. It's a very subtle interplay. So we need it, but then how much we have does also not tell us too much. It's really this feature that the quantum circuit needs to be able to get rid of the entanglement again. And the same happens actually if you look at the non-stabilizerness, so now there are many curves are there on top of each other. Here we see that so now here maybe they have different system sizes, so maybe there it's a bit clearer, no, because the non-stabilizerness actually increases with system size, so we need to build up more of that, and then we see, but for a given system size somehow these are different also sweep speeds for different numbers of layers. We see that some of the maximum is always similar, but then it also how much we go down in the end depends on how many layers we give the system to do this. And so also there is a sort of, so we have these sort of barriers. We need to build up these quantum features initially, and then we need to get rid of them again. Okay, and in this case, actually, we saw that we also find a heuristic scaling law. It seems to be some universal behavior actually there in this non-stabilizerness. Okay, so yeah, so what we see here is that these tensor networks, they give us a powerful tool to try and understand how much quantum features actually do we build up or do we need in quantum computations. Okay, so that's I think a very, very interesting, a very important way of using them. Also, okay, a little bit slow, but also want to show a second point, namely how we use them for many-body systems in the context of elementary particles, and this, so these people who worked on that. Okay, let's see. So, what is the main idea here? So, elementary particle physics or high energy physics, what they're interested in, yeah, how do elementary particles work? And so, to do this, they have huge collider rings. No, they smash heavy ions into each other. And then they have enormous detectors. This is like a person is this big somehow. So this is enormous detectors, and then see all the types of particles that come out of this collision. And then from the trajectories of the particles, they try to understand what happened actually in the collision event in this fireball that they have generated. Now, to understand what is the type of model that we need for this? This is for the elementary particles, this is the standard model of particle physics. We have leptons, quarks, gluons, and so on. And for these collisions, we need, to describe them, we need quantum chromodynamics, which is an SU3 gauge theory, which describes the interplay between quarks and gluons. Okay, so this is what determines what particles come out here mostly. Okay? This is the thing that we should solve, but actually QCD is very, very hard. But there are actually simpler gauge theories there also, like quantum electrodynamics, which has a U1 symmetry. And I would like to use, so what we want to learn something that is relevant for these heavy ion collisions, but I try to explain you a little bit what is actually the gauge theories, or how do we, what are these theories of interest by the example of QED. And then we're going to see some interesting physics results that you can compute. Yeah. Okay, so what is QED? QED describes the interaction of charged particles, electrons and positrons with the electromagnetic field. And so essentially this is the Hamiltonian. Maybe if you've never seen it before, it may look a little bit daunting, but it's actually so difficult also. So what we have here, there's some fermions, this psi dagger psi, with a strength m. So this is just counts how many fermions there are. This is the rest mass of electrons and positrons. Then they have a kinetic energy. So there's a derivative over there. So they can move dynamical particles. But now they should be charged particles, which means there's an electric field from the positron to the electron. And the field has some energy, E square. Okay? But now what is the interesting part is, well, if the electron, for example, moves, the field should not just stand there and watch the electron, but it should adapt instantaneously while the electron moves to the new configuration. And this is given by this minimal coupling here. So we can define this mathematically, that this model has a gauge symmetry, a local symmetry, which means there's a local unitary operator, e to the I alpha x gx, generated by the Gauss law operator. Essentially says the divergence of the electric field is equal to the charge density. Yeah? So what does this mean? if I have a positive charge, field lines come out. If I have a negative charge, field lines go in. So there's a sink of field lines, and I cannot have things like this. The electric field goes and then somewhere stops in the vacuum. So this is not allowed. And if this looks complicated, then I think many of you have probably seen this actually in high school or so, where we have two oppositely charged capacitor plates. One is positive and one is negative. And so there are field lines that go from one plate to the other, and they don't stop somewhere randomly in space. Okay, so this is these are grains that in some viscous liquid that orient along the field lines. And so this is something that more or less maybe you've seen. And so this is for quantum electrodynamics, but we can just generalize this. So a gauge theory is essentially any Hamiltonian where you have a unitary operator that acts locally. So that for all x, for all positions in space, there is such an operator. So it's given by the elements of the gauge group. And so if you apply this unitary, it's a symmetry of the states, all physical states don't change if I apply this unitary transformation. It's instead of a global symmetry, something that acts only locally. And now this thing has, okay, there's actually, by the way, in the tensor network community, there's a huge effort because now this means we have the symmetry here, which means there's an enormous number of redundant states essentially. And so there's a huge effort by groups like also Frank, Mari Carmen, and so on, to write down tensor network states that respect this symmetry explicitly and to make them more efficient and so on. Okay, so now having this gives us actually deep physical consequences, because now let's look at what happens if you have the electron and positron. There's a field line between them, so we try to pull them apart, which means that the farther they are apart, essentially the more energy I put in the electric field between the two of them. And so if I plot the potential energy goes sort of linearly as a function of distance. And you can really think about this as a spring that you stretch more and more. But actually there's a competition in this Hamiltonian, because now it's a quantum field theory. So these particles, they are not given and fixed, but they can actually pop out of the vacuum. And this is and so they have a certain rest mass, but then I can generate electron-positron pairs. And at some point, if I stretch the spring too much, this string will break. And so there's a new electron-positron pair that pops out of the vacuum, and they move close to the other charges and screen the field. And so they have mesons of electrons and positrons. And then the potential energy, so at first it goes linearly, and then it breaks and becomes flat. And so in QED, this happens actually in 1 dimension, in 3 dimensions. We do have free electrons, so the system becomes deconfined. But the interesting thing is that this is something that happens in all these gauge theories because of this strong interplay between the charges and the field. But in the quantum chromodynamics, this is something that is the one that we really don't understand, because we don't have a good description of the theory. It's very non-perturbative and it's very heavy numerics to try to understand the confinement problem. And if at high temperatures things become deconfined, or how do they become deconfined? Is there a critical point and things like this? So it's one of the outstanding questions of high energy physics. Okay, now we can try to compute this. We can do this in not in QCD, as I mentioned, it's too hard, but we look at the dihedral group. So we take a non-abelian group, but the symmetry now is not the Lie group SU3, but D3, for example. So the symmetries of the triangle, which is nice because we can have just a few states. We can easily tackle this Hilbert space. And then we look at the string breaking. So we compute the ground state energy. If we don't have any probe particles, then we put 2 particles in there, and then we put them farther and farther away. And then we see how much energy do we put into, okay, I will go 2 minutes over time. How much energy do we put in there? Okay, and so at some point, the string will break. There's no connection anymore, and then some effective particle here and some effective particle there. And that's actually interesting. These particles that pop out in this theory, they are called glue lumps. They're a bit exotic. They don't appear so much in QCD. So we can now see this as a bad thing because maybe it's not so relevant for real nature, but we can see it also as a good thing that we can probe exotic particles. And okay, so then we can compute the interaction potential between the two by looking at the energies when we have the particles as a function of distance. And we compute this with DMRG. And we see that, so this is now the potential. And as I said very hand wavingly before, there's a regime where the particles, have a string between them, they attach to each other. And if I stretch them more and more and more, at some point the string breaks. And now I have one glue lump here and one glue lump there. And after that point, I can just move them apart as far as I want. Yeah. And so this is nice that we can do this with DMRG, because we can now do a really interesting analysis. We can see how much does it depend on the coupling strength, the interactions, and we define this as scaling with interactions, and we can do a continuum limit scaling and so on. So we can really try to get quantitative answers also in very strongly non-perturbably interacting regimes. Something that in other ways I think will not be possible. And with this, I come to my conclusions. The chairman's getting a bit nervous, but okay. So I've shown you two examples. They're very, very interesting application areas, of course. We've seen an example from elementary particles where we see this confinement problem that we can, in simplified toy models, but still where we can get some interesting insights. We can treat them. There's also, just I want to point out, there's an effort in my group also to understand in general, coming back also to the emergence and so on. So how can we actually relate chaotic phenomena to the appearance of quantum effects, to entanglement, non-stabilizers, and so on? Which is, Ganesh is sitting in the back. He is happy to answer questions about this. We also looked at benchmarking quantum computers now in Quaoa. We also tried to see, can we compute interesting correlations in optical lattices? So we do also toy models in one spatial dimension to measure how non-Gaussian do these come. Again, Ganesh is the person to talk to. And with this, so I just want to point out that the tensor networks are very, very nice, but what I, from an application point of view, would like, is to have also the possibility to have really longer ranged interactions in the ground state. There's some very, very interesting models, but they have infinite range interactions. And of course, finite temperature is also an interesting question. And one thing that I've only hinted at, but I think it's very, very interesting also this question to use tensor methods to characterize these quantum features. And we have seen, for example, for GME yesterday, an interesting talk, how one can use this, but also others, no, of course. I've not seen all the talks, I apologize, because I came only yesterday afternoon, unfortunately. Okay, but so I think there's interesting also methods that one can use to characterize quantum feature using tensor methods in general. And with this, I thank the team and I thank you. Yes, exactly. No, so if you are interested in entanglement across a specific cut, then the geometric measure of entanglement is fine. No, it tells you how much entanglement you have there, and it's all there is. But you could also, from a many-body perspective, you can wonder, like this example where I showed, no, where you have, you can, well, try to distinguish how many particles are actually entangled with each other. So it's not, so there's what one calls the depth of entanglement and the breadth of entanglement, no? It's more about this question. So how many particles is the entanglement spread out? So to say it's a question about the correlations, so how they are spread out throughout the system, and not about how much entanglement to have at a specific cut. No, but that's so actually the entanglement in a many-body system is usually fairly localized because you have so if you have a finite correlation length, then within a certain correlation length, of course, systems are very local. No, but that's true. Yes, indeed. But so you would still okay, let me think for a second. So you because you, I mean, okay, there's of course different measures also for multipartite entanglement. So now we have to be also careful to not confuse them. So I would guess, let's see. Okay, now I don't want to say something wrong, but if you have finite correlation length, I guess you would find. Okay, but you're saying if I take any cut somewhere, you have locally some sort of Bell pairs, and so you will not see the difference, right? This is, I guess, if I want to. I have to think for a second about this.
Any other question?
So, for example, the kind of question that is the degree respective distance. So how many points realign minimum distance? How does this kind of distance fits? Are there interested for geometric measure?
This I would be very interested to understand if there's if one can use these things. Yeah, I don't see it immediately, but I think this could be an interesting point. So this also, yeah.
Just considering distance, and then you can put how many points.
Exactly. Yeah. So I think so. I don't know the answer, but this is also one reason why I wanted to show this is because I think there could be interesting things that one can learn and maybe draw connections.
Much louder.
Subsets. This one, for example. What are these subsets? Yeah. Okay, so this set is are the n separable states, so all states where I can which are separable across any cut in the system. Okay. Then I have actually I forgot the 4 separable states. It's a second variety, exactly. Yeah, I guess. And then we have the 4 separable states, which I just realized before that. First, which would be where we can cut out where 2, for example, are in a Bell state and the other 3 are separate. And then we have 3 separable states would be where I can have 2 cuts in a system of 5. Okay, so I have you can write your state. So the k-separable states are where you can write it in anywhere like this. So you bunch together a certain number of particles in k, in the tensor product of k vectors. Okay, and so sorry? Is it there?
The rank.
Rank. Not yet. Yes, exactly.
Every time that you don't have the separation, you cannot separate anymore. You cannot add extra tensors.
Yeah, it's not exactly the rank, no, because you could have. So if you have, for example, in the 2 separable states, this one. So okay, across this, you have tensor rank 1 if you look at particle 1, 2, 3 times, maybe I can try to.
Right, that simple doesn't that to be the sum of three? It to be the sum of all in one.
So if I have something like this, no? So if this is my system A is 1, 2, 3, and my system B is particle 4, 5. Then, so this is a two separable state, no? And there's tensor rank 1. But another state could be where I have, for example, just the first particle, and then I have some state on 2, 3, 4, 5. This would also be, then A is just the first one, and B would be 2, 3, 4, 5. This, yeah, this you can, yeah. But so
It's one that we actually have a
yeah, exactly. No, exactly. Yeah. It could be also that you have a state psi 1, 4, 5 versus psi 2, 3, right? Something like this. Exactly.
I don't know. You have everything of dimension 2 or like this thing you can detect in dimension 2.
Yeah. So it could be, yeah.
If you have a state and you restrict it to like randomly to dimension.
Yeah.
If it didn't have this property before, couldn't write this in this way.
Okay.
Okay,
That's
become separable.
By truncating the, yeah, okay. Okay, that's but in principle, like the definition, the entities could be d-dimensional, so they don't have to be qubits from the outset, but
then to detect these properties enough.
Yeah. Yeah. Okay.
Each of these circles is like set up, right? It's like certain rank strata, right? Say like I have different cuts, and then the three circles are just 2 rank 1 with certain patterns, and then any of them, and then also don't fix the one dimension and his parts.
Exactly.
The one dimension is obviously also limited to filling the ambient space. It's like a well-defined set of varieties in each of these.
Yes.
States.
Yes.
Yeah, in fact, like
Exactly. There's some, but there are many, which I guess makes in general also a little bit difficult this measure, because you should look at all the different varieties in principle and then look at the distance to any of these.
Any other questions?
I take products. And I do lot of rotations.
What if I do natural orbital like rotation? What is orbital rotation about?
So what do you mean? Sorry.
That maybe I can discuss. Basically, let's say, what is the smallest transformation I can do to create some a